let's do some Leetcode. Before I do though, I'm going to do one monkey type session. Alright. Sure. Now for some neat code. What I'm gonna do is open up a NeoVim terminal on the side while I look at this question. So maybe I'll extend it down so I can get the, it's gonna be this whole thing. And I'll just put my terminal next to it. Okay. You're given an array of integer nums and an integer k. There is a sliding window of size k. It starts on the left edge of the array. The window slides one position to the right until it reaches the right edge of the array. Return a list that contains the maximum return a list that contains the maximum element in the window at each step. We got k. What is k here? Right. Our window size. So I could say that, you start R at k. Right. Let me think. Let me just think for a minute. The largest number is 2, 2, 4, 4, 6. While R is less than N. If R is less than N, once it reaches the end, the R would be there, but then you'd still need to process one more. So that might be an equal there. Okay, and then, for each of those windows, what do you do? I guess the brute force approach would be trying to consider what would be the brute force approach here. You have the window, right? So say it's nums. of L to R, but this R is not included. But when it reaches N, zero, 1, 2, 2 means it goes to, it doesn't include it. But N is the len. So maybe then this just doesn't make sense. L to R. Maybe I'll just print what this looks like, just to sanity check. Name error, list not defined. There we go. Did that even work? Hello? Oh. Oh man. Let's try with the given solution, namely 1 backspace. Alright, it's this one. 2, 3 backspace, 1, 0, 4, 2, 6, and close the braces, and a 3. Of course, what am I thinking? I really don't know how to do this, huh? Let me think. Okay. Yep. Can't even stop it. Well, that terminal's gone. Alright, there we go. Sliding window. New line. Left and right pointers increment. Plus equals 1. We're gonna have to put a colon. One, 2, 1, 2 and 0, 1, 4, 0, 0, 4, 2. And then technically it should go one more, so. The problem is with that is I'm not sure if that would error or not, which it doesn't. What do I even do here? Like nums LR, find the biggest number out of these, right? So that would be my brute force approach. Alright, well, I did it in the brute force manner. Now, since this is a hard problem, I don't reckon that's the right solution. And from the looks of it, you know, you do a m times k. It'll be an n times k big O of n times k. So you want to change that so that it might just be big O of n. And the only way to do that is if you keep track using some variables rather than doing a max. And the only way to keep track of stuff let's have a look at how we would do this. 1, 2, 1. One, two, one, 2. So you keep track of the max being 2, maybe. And then you look at the 0. Throw out the L. So 2, 0. Compared the 2. The 2 is greater. Still. Now if you throw away the 2 next, you don't have a max anymore. So the new max or you don't throw away the 2 yet, you throw in the 4, you define the new max, throw away the 2. Go across again, 2, is it a new max? No. Throw away the 1. If you have, then you go to 6, alright, that's the new max. You throw away the 0. And then in the scenario where, say you go the opposite direction, where you go 6, 2, 4, the new max is 6, you throw away the 6, oh sorry, you add the 0, it's not a new max, you throw away the 6. But then you don't know what the next max is unless you also just keep track of the next max. So you have, you know, a max, a next max, and if you throw that away, I guess the other problem is the next max. If they are equal, if the next max has multiple options such as the 1, then you want to somehow, you know, group them together to be the next max. And the next max, it's going to be a problem. Alright, well, I've made the brute force approach. Yeah, let's have a look at the solution here.
Hey everyone, welcome back, and let's write some more Leetcode today. Let's look at a sliding window problem, a hard sliding window problem, sliding window maximum. The statement is pretty straightforward actually, so we're given an array of numbers, and we also are given a number k, which is going to represent the size of our sliding window. It starts at the very left and then works its way to the right, and so since its size k, there's only going to be k numbers inside the window, and for each position that the window is in, we want to return the max value. So you can see that this is our input array, and our window is going to be size 3. So this is our first window, and the maximum value is 3. So then we see, and then we add a 3 to our output array. So the output is going to be an array. Next we see that this is the next position of the sliding window, and the maximum value in this case is still 3. So we put a 3 in our output.
Oh, actually, I just realized people have been speaking and stuff. Hello to the Abdurraham. Ramen, my bad. And the Indian Outcast. So the Indian Outcast says, "What the F is that? I've never seen such a keyboard." Yep, it do be like that. It's an Ergo keyboard. It's called the Glove 80, and yeah, I just use it. And also, you might hear noises in the background, so sorry about that. Anyway, I'm gonna continue reading on the sliding window.
And the next position, we see that this is our window. The maximum value is 5. So we put a 5 in the output. Now, you might recognize one solution to this problem immediately. For each of these windows, why don't we just scan through the array, right? Like, it's pretty easy to find the maximum in an array, right? Like, if we had 1, 2, 3, we just check every value and see, okay, this is the maximum. And then we just shift our window by 1 into the next position, right? And we keep doing that until we're done. Well, the time complexity of this is going to be roughly, since the size of our window is k, how many windows are we actually going to have? Let's say the entire input is length n. In that case, we're going to have roughly k times n minus k. That's how many windows we're going to have, right? And so this is going to be our time complexity. But I'm asking, is there a better solution? Can we actually make a linear time solution where n is the size of the input array? And the answer is yes. And I'm going to show you how to do that right now. So I'm going to show you the best solution, but one thing you have to notice first is this. So let's say this is our input array. We have 4 numbers and our window size is going to be 3, so k equals 3. Notice how these values are in increasing order, right? 1, 2, 3, 4. Okay, so we notice that. Now look at our first window. We have 1, 2, 3. We see that 2 is greater than 1. We see 3 is greater than 2. Now that's good. And so we scan through every element. 1's not the max, 2's not the max, 3 is the max. So then in our output, for the first value, we're going to put a 3. Okay, and that's great. Now we shift our window to the next position. So now I'm literally just going to repeat that process the brute force way. Now I'm going to check 2, okay. Now I'm going to check 3, 3 is greater. Now I'm going to check 4, 4 is the greatest. So we add 4 to our output. And so then we're done, we have our output, but we just did it the brute force way. But do you see the repeated work that we just did? As soon in our first window, we saw 1, 2, 3. We know 3 is greater. So we basically eliminate 2 and 3. And then when our window is at the next position, it's over here, right? 1 is no longer a part of our window, so we don't need to worry about 1. What about 2? Well, 2 is inside of our window, right? It's at the leftmost position. But since we know that this 3 is greater than the 2 anyway, why would we ever need to look at the 2 ever again? It's never going to be the maximum. And let me just make it even more obvious. Let's say our window size is 6 and this is our input array. Okay, so for our first window, we have to check, okay, the 1, another one, another one, another one, another one, and then a 4.
So we're basically
4 is our
sorting it
max.
before we
That's
even
great, so we can
look
save
through the
that.
array.
And then we shift our window to the next position and see we're repeating all that work over again, the 1, 1, 1. As soon as we see this 4, we know that these elements, as far as we're concerned, are useless to us. We never have to look at them again. They will never be the maximum inside of our window, because our window is going to continue being shifted to the right position, and the 4 is still going to be in the window even after these elements have been eliminated. And so the data structure we're going to use to eliminate these values is a DEC, or a DQ. And I'm going to show you the algorithm. And just to repeat myself, basically what I'm saying is, if we have a window and we see a value that's greater than values that are previously in our window, then we can eliminate those values from our window. And so I'm going to show you the algorithm, and what you're going to notice is that the values in our DEC are always going to be decreasing order. So this says decreasing. So we know our sliding window is initially size 6, right? K equals 6. So we're going to take the first one, put it in our window, the second one, put it in our window, and then just repeat that, right? We have 5 ones. We're going to add all of them. And then
This being a
get
DQ problem is
4.
actually
so since
interesting.
4 is
I would have thought
greater
sorted
than the value
list.
at the top of our DEC, or at the rightmost position of our DEC, what we're going to do is we're going to pop this value off. What we're going to do is pop the top of the DEC, right? And now we're going to make the comparison again. We see there's still a 1, so 4 is still greater than the top of our DEC, so we're going to pop. We're going to pop this, we're going to pop that, we're going to pop all of them, and after that, we're going to add the new value 4. And so what are we going to add to the output? So we have an output array. What value are we going to add to it? Well, the leftmost value, and in this case, we only have one value, is going to be what we add to the output, so a 4. And so we're done with this comparison. We don't have to look at it again, and we don't even have to consider these elements anymore. And now we shift our window by 1 position. So we're introducing a new element, 5. So before we add the 5 to our DEC, what do we have to do? We have to check, is 5 greater than the value at the top of our DEC? It is, because the top value is a 4. So why would we ever consider the 4 as the maximum value ever again when we know there's a 5 right next to it? The answer is we don't have to, so we remove the 4 from our DEC. And then we can add the 5 to the top, and then we know that there's only one value in our DEC, and it's also the leftmost position. We are going to add that to our output, and now we're done. This is our output. But what's the time complexity of this algorithm? First, we took each one, added it to our DEC, right? We did that for every single value. That was expensive. And then we also crossed out. We had to remove every single value from our DEC. But adding and removing, we know adding and removing is an O of 1 operation to our DEC, and we had to do that for every single value in here potentially, but that's still O of n, right? The result is O of n, which is why this is a really good solution. And I'm going to show you one last example. And by the way, this is called, the type of problem this is called a monotonically decreasing queue. And the reason is because our queue is always going to be in decreasing order, which this next example is going to demonstrate. And the reason we're using a queue rather than a stack is because we want to be able to add and remove elements from the beginning in O of one time. But not only that, as our window shifts, like for example, our window's here, next our window could be here, we want to be able to take an element like this and remove it from the beginning. And we want to be able to do that in O of one time, which is why we need a queue. So let me quickly just run through this last example. So we have our first window over here, 8 and 7. So we add 8 to our queue. Then we look at 7. Well, 7 is not greater than 8, right? That's just not true. So we're allowed to add the 7. We only want to remove smaller elements if they exist. But in this case, that's not true. So we add the 7. And notice how these values are in decreasing order. We have 8 and then we have a 7, right? They're in decreasing order. So what that tells us is since we want the max value in our sliding window, we can just look at the leftmost value in our deck and then add that to the output. So I'm going to add 8. For the first sliding window, the max value happens to be 8. Okay, now the next sliding window, we have 7 and we have 8. Okay, the first
This is such a smart solution.
The 8 is no longer in bounds. So we got to pop from over here, right? And we want to do that efficiently, which is why we're using a deck. But so before we add anything, we pop. Next, we see the 6. Well, 6 is not greater than 7. That's not true. So we're allowed to put a 6 here to keep this in decreasing order. And now the max value in this window is 7, which is the leftmost value in our deck. So we add it to the output. And lastly, we look at the last sliding window, which is these last two elements. And we know that the 7 is no longer in bounds, right? So from the leftmost position, which is this, we pop from our deck. We make one last comparison, right? We just added a 9. Let's take a look. Is 9 greater than the top value of our stack? Is it greater than 6? It is. What does that mean? That means we have to pop from the top of the stack, the rightmost position, or rather the queue. I don't know how many times I said stack, but we're going to pop from the rightmost position in our queue.
Just gonna write some stuff about this question. So sliding window maximum. What in the world just happened? Why did that not save? Whatever. Sliding window maximum. So from, I think how I did it with the previous ones, I would just put some tags as well. DQ. A queue. Is that not what you'd call it? Alright, DQ. Sliding window. And it's an array, but those are like the things that I've used. Okay. With all that said, you make use of a monotonically decreasing queue. Okay.
And now we are allowed to take the 9.
After I finish writing this, I'll
append
attempt
to
it
our
before
queue.
even looking
So
at
we
the
add
solution.
The 9 now. We know that this is the
I just need to know what
queue, and we know that in
Python
this window,
thing they use.
9 is the maximum. So we did this correctly, right? So we can take the 9, add it to our output. So this is the result that we're looking for. And I hope this demonstrates a few of, like, when you actually run through examples, it shows you like what you need to know. It shows you why we're using this data structure, and it shows you why it's so efficient. So now with that in mind, the coding solution is not too bad. So we are going to have an output array to put the values in. We're also, for our window, we're going to have some pointers, so left and right pointers. These are going to represent where our window currently is. They're both initially going to be set to 0. And we're also going to have a queue. In Python, we can do collections.dec. And so we're going to run this until...
There we go. Alright, so that's what I was looking for. So it's literally called DQ. That's why we'll have a queue. So they also said make this 0 initially and have a queue equal to DQ. And alright, so I think I should be able to figure this out. Let's see. If I can't figure it out in 10 minutes, I'm going to actually look at the solution. Okay. So, take this step by step. For the left pointer and the right pointer, okay, so the left value, the right value gets incremented, so we have to first put q dot, it's either add pop, push pop, maybe it's push pop. Push pop is a I think it's push pop. Let me just see DQ. Man, I can't even write. Append left. Is that really what it is? Using append to insert element at the right. Append left to insert element at left and insert 6 at the beginning of DQ. Um. Okay. Pop to delete an item from the right end, pop left to delete from the left end. Okay. So if that's all it is, append and pop. What is this? Insertion. Counting. Okay, sure. Go back to my other window.
Our right pointer is no longer inbound.
Okay. Q.append. Append that number. You append that number.
So while right is still in bounds, so we want to our queue, we want to be able to append.
Ooh, maybe I'll just write.
The value, this value, right, r, and instead of doing nums of r, I'm just going to do the index itself. So this is going to contain indices, because we know we can take an index like r and then easily find the number that it maps to by just taking nums of r, right? But before we're even allowed to append a value to our queue, we have to make sure that no smaller values exist in our queue. So while the queue is non-empty and the top value in our queue, or the rightmost value in our queue, is less than the value that we're inserting, nums of r, which is the current index we're at. So while smaller values exist in our queue, we just want to pop from the queue, just remove values while that condition holds. And only after we do that are we allowed to add the new value to the queue. We also, if the left value is out of bounds, then remove the left value from the window. So if our left index, left, is currently greater than the leftmost value in our queue, then we can pop from the left of the queue. So basically, we know left and right represent our window. So if our window is if this value, the leftmost value in our queue, is out of bounds of our window, we're going to remove that. We have to remove that. And this part is kind of an edge case. Since we are starting at our window being left and right both being at 0, we have to check that our right plus our window is at least size k. So if we want to update the output, we have to make sure our window is at least size k. So that's basically what I'm doing here. And for each iteration of the loop, basically for each window, we want to append our output with the maximum. So we know the maximum is the leftmost position in our queue, and we want not the index, but we want the actual value itself. Don't forget, like me, to update your pointers. So we know right is always going to be incremented. So at the end of our loop, we can increment right. Left, though, is only going to be incremented once our window is at least size k. So we're going to put that inside of this condition. And now the only thing left for us to do is return that output. And it works. And we know that this is the most efficient solution, with the time complexity being linear and the memory complexity also being linear, because we are using a data structure, our queue. So I hope this was helpful for us to do.
Yeah, okay. Let's just try and rebuild this from that point onwards. So G 18G D. Okay. Let's go. Initialize Q collection, so Q DQ and it's in index form. While R is less than len of nums pop values from Q, while Q and nums Q minus 1. Is less than nums R. Remove left value from the window. Removing the left value from the window only when Q of 0, the first position of the Q, the left pointer is greater than, you just have to, yeah. If R What in the world did I just do? Output append the value on the left. L is plus equal to 1. Yeah, okay, well that makes sense, right? You're just getting rid of the left side. Okay. Yeah, alright. I mean, this is done. This I feel like could be done better, code-wise. But I'm too lazy to do that right now. So I'm gonna just submit the solution here by rewriting it. Alright, practice some of my, you know, typing. Issue is I can't type here. Oh. Yeah, okay, it's just a me problem. Sorry. Okay. L equals R, which equals 0, while R is less than len of nums. Why is that the way it is? Whatever. It'll still be fine. It won't be fine, but let's see. Doesn't even move it across. Alright, we're gonna put a space there. It doesn't even, okay, wait, okay, no, I did that wrong. Yeah, okay, there we go. Q0, pop left. 0. No, I keep on hitting wrong numbers. Zero, 0. Yeah, okay. Run. Gratification. I'm gonna go to actual sliding window problem, sliding window maximum. Where is it? Where is it? Sliding window maximum. And then I'm gonna just complete it on Leetcode as well, you know? I'm guessing that was all right. Yeah, I can't tell. Shift Z, okay, yeah, it is. All goods. Man, AI is everywhere now. Analyze complexity. Alright. I was just gonna write a little bit about this. Leetcode on 2 pointers. Sorry, sliding window. Okay. I'm good with that, and yeah, we can close that. Alright, let's just do one more of this. I keep on slamming the wrong values. Okay. Alright. Cool. Cool. Alright. I'm gonna probably go and just eat some food before I come back again. Just gonna eat a banana or something. So, BRB. I should just write it down. Um, just put the B up top right, I guess. Okay. Oof. Keep it as is. Alright. I'm gonna just try to keep my iPhone charged, so that's what I'm using for my overhead video. Right now it's 58%. Okay. And I gotta connect this to a cable, which I have right here. You can't see it. Oh, that moved a lot. I hope that was alright. Alright, be right back. Was alright. I hope that was alright. Alright, be right back. Alright, your boy's back. Okay. Right.
不知道敢不敢进去洗手？
就看一看吧。
不敢。你打开了，我这一下给它吹风，吹到外面来。
Alright. Let's do one of these. What? Why is all my stuff logged out? Alright. Give me a sec, guys. Okay, I'm logged in. Alright. Yo. Well, that was alright. 51 words per minute, that's pretty good. There was something that I was going to do today as well. In just a moment, so I'll be right back. q of -1. Q of -1. What would I do with this q of -1? Oh, I still have the... Wait, do I still have the BRB? No, I don't. Okay. Just trying to understand. What do I do? Opposite. And we're saying there's only like yeah, okay. If you go left and right, left and right, left and right, opposite. Yeah, there's a few different ways I could go about this. Yeah, it's so simple that After you peek at something, what would I even say here? Q, append, L. And break. No, continue. I think that worked. Let's try a different one. No. Okay, well that didn't work. Wait, I didn't even... Did I write it? I don't know. Yes, that worked. Okay. Okay. Yippee! That worked. Map this to that, this to that, that to that. I mean, yeah, that would make sense. Stack.append, .pop. How do you actually... So you can just pop any list? Is that really the case? I was thought you had to use DQ. Might not even be the case, so... List Python method. Pop method. I did not know you could just pop on a list. Oh my god, that would have been... I don't even need to use DQ there. Like, man, I should have just known, to be honest. Alright, let me just watch this video.
Hey everyone, welcome back, and let's write some more neat code today. Today let's solve an easy problem, valid parentheses. This is such a common interview question. I think I've been asked this so many times, like in phone interviews and online assessments and stuff, so definitely a good problem to understand. We're given a string S containing only these 6 characters. They're basically parentheses type characters, right? Brackets, parentheses, closing, and there's 3 pairs, so there's an opening one and then there's a closing one. And that's true for each of the 3 types, right? Open, and close. And our only goal is to determine if the input string is valid or not, and it's valid if the open brackets are always closed by the same type of bracket, and if the brackets are closed in the correct order. So if that's true, then it's valid and we can return true. If it's not, then we can return false. So first example, now is this valid? Well, we start with an opening parenthesis, and then we close it with a closing parenthesis. So it happened in the correct order, right? This was closed in the correct order. Every open has a matching close, so this is valid, so we can return true. Obviously, if the order was opposite like this, it would not, we would have to return false, because first of all, this opening bracket isn't being closed, right? It's never being closed. The closing needs to go on the other side of it. So we have some unclosed parentheses, and it's basically in the wrong order. Let's look at this other example. We see, okay, opening parenthesis, then it gets closed, right? Okay, now we don't have to worry about these two anymore. Opening bracket, and then it gets closed, so we don't have to worry about that anymore. Opening curly brace, and then closing curly brace, so we don't have to worry about that anymore, because they were all closed, and they were all closed in the correct order, so we can return true. What about something like this? See, we have an open parenthesis, and then we have a closing parenthesis, right? So then this is closing this one, and we have an opening bracket, and we have a closing bracket coming after it. So, right, this closes that, but this is wrong, right? This is not valid, and the reason is the order is off, right? We see that this closing parenthesis is actually being applied to this open bracket, but these do not match each other, right? So these don't cancel out. So this doesn't work. Basically, the order is wrong, and that's pretty self-explanatory by looking at it, right? It just doesn't look right. So now how can we actually determine an algorithm to be able to solve this problem? Well, one of the first things you might notice is we have to start with an opening parenthesis. We can start with this, we can start with an opening bracket, or we can start with an opening curly bracket, but we can't start with a closing parenthesis, right? Because this is never going to be valid. We can't add any more stuff over here that's ever going to make this valid, right? It's not being applied to any opening parenthesis, so we can't start with a closing parenthesis. We have to start with an opening parenthesis of any kind. And once we start with an opening parenthesis, we can pretty much add as many opening parentheses as we want, as long as we're eventually closing them, right? So if we have 4 open parentheses, we have to have 4 closing that come after it. As we add a closing parenthesis that matches, right? So these two match each other, they counteract. We can then remove them from consideration, right? We can remove them from our list, right? So now let's say we get another opening parenthesis. We see it's being applied to this one, right? And we can remove these two as well, and we can keep doing that. So remove this and this, and add one last closing parenthesis so we can remove it along with that, right? And once we're done removing that, if at the end we have an empty list, right, like this, let's say this is our list and it's empty, then we know we can return true because we closed all our opening parentheses, they matched each other, and everything went gray. Also, notice how as we add closing parentheses, right, so this one, and then we have to remove from the beginning of our list, right? So now let's say we removed these, right? Now let's say we get a closing bracket. Okay, we got to remove it, and we have to remove this one. So we're always going to be removing from the end of the list, or the top of the list, or the top of the stack. So that's basically a hint for us that it's going to be helpful for us to use a stack data structure to solve this problem, because as we're closing a parenthesis, right, let's say we add this closing parenthesis, we're always going to be popping from the top. A closing parenthesis is always going to be matched to the most recent opening parenthesis. And let's say we have these 3 opening parentheses in a row. Let's say next we get this closing parenthesis. How do we know these two match each other? How do we know this closing parenthesis is able to close this one, right? How can we basically check, how do we basically match every closing parenthesis to the correct opening parenthesis, like this basically? And this closing bracket needs to match to the open bracket, and the closing curly brace needs to match to the open curly brace, right? So I hope you guys can see what I'm doing up here. This is basically going to be our hash map, actually. This is going to help us determine if a closing parenthesis matches an open parenthesis, right? Basically just the correct type. right? So let's say we had this closing parenthesis, right? We'd go up into our hash map and check, okay, this closing parenthesis matches this open parenthesis. Okay, well, what was at the top of our stack? This is at the top of our stack, right? This other closing parenthesis. So since they do match each other, we can cross them out. We can pop from the stack, right? Now let's say we get this closing parenthesis, right? Well, which one does this match to? We go up to our hash map and check, okay, it matches this one, right? This closing curly brace. Okay, let's take a look at the top of our stack. Hey, that's exactly what we needed, right? This closing is what's up here. So they do match each other. We can cross both of them out, right? And let's say lastly, we had a closing bracket. Okay, same process, check in our hash map. It matches this one. Is that what happens to be at the top of our stack? Yes, it is. So we can say these two match each other and remove them from our stack. And now let's say now we're done. Our stack is empty. We have an empty list. We have nothing left anymore. That means all the parentheses matched each other in the correct order, and we can return true now. So with that being said, let's jump into the code. And FYI, this algorithm is big O of n because we're only having to go through every input character once, right? We're just scanning through them. It is also going to take big O of n memory because we're using a stack. The stack could be up to the size of the input, which is n. So time and memory complexity is going to be big O of n in this case. Let's go to the code now. So remember, we are using a data structure, a stack, or in this case, it's just a Python list. Also, we're going to be mapping the close to open parentheses. We're going to be using a hash map to do that. So you can probably tell what I'm doing. I'm just going to take every single closing parenthesis, so like this one, and I'm going to map it to the opening version of that parenthesis. And I'm going to do that for all three types. So we had the closing bracket. Let's map that to the open bracket, and closing curly brace to the open curly brace. So these are our three pairs, 1, 2, and 3. Now let's start actually building up our stack and popping from it and just going through every character in this input string. First, let's check if this character is a closing parenthesis. So if this character is in close to open map, that means it's a closing parenthesis. And the reason why is because the keys, every key of this map is always a closing parenthesis. So if this is a closing parenthesis, we want to make sure that our stack is not empty, right? We cannot add a closing parenthesis to an empty stack, and we want to make sure that the value at the top of our stack is the matching opening parenthesis. So let's make sure so in Python, stack of -1 is the last value that we just added in the stack. Let's make sure that that is the matching open parenthesis that we need. We can get that by taking our map and getting the character and getting the closing character from it. So we can basically, that's what we're doing. We're passing in the closing curly brace, getting the opening curly brace or whatever where we need. If these match each other, that's good. That means we can pop from our stack and then continue going. If they don't match each other, or if the stack happens to be empty, that means we have to return false, because that means our parentheses don't match, right? Obviously, we know this is not a matching parenthesis. Having just a closing parenthesis to start us off is not matching. Also, this is not matching, right? Having a closing parenthesis with an open bracket, this is not matching. So that's why we would return false. Though if we don't get a closing parenthesis, that's what this condition is for. So if we ended up getting an open parenthesis, we know the rule for having an open parenthesis is we can add as many as we want. So if we get an open parenthesis, we're just going to take that character and then append it to our stack and just keep going. So remember, at the end, once we've gone through every character, we can only return true if our stack is empty. So if not stack, then we can return true. Otherwise, we return false. So this is the solution code for this problem. I hope you understand why we're using a stack data structure, and I hope that this map makes sense. This map is just a little shortcut for us, and I hope that this was helpful. If it was, please like and subscribe. It supports.
What are we saying, bro? What's the problem? Opposite L is the problem? Hello? Just need to understand this. What is the problem? Alright, well, let's run these test cases. I'll be able to see the errors. Or not. Oh. Key error. Oh. I can understand why there's a key error. Wait, then doesn't that mean what I wrote would also not work? Ain't no way. Min stack. Alright, let's do one more and then I'll call it a day for Leetcode. You want to design a minimum stack solution. Min stack designing, probably. And no submissions. Alright. And you're telling me this is also a Leetcode question, so. Damn. Leetcode. I didn't know you'd do questions like this. I didn't know Leetcode would do questions like this. Alright, that's good. That's good. I thought it was all Doom. It was all Doom Eternal. Just gonna put on Doom Eternal while I. Should I actually? That would kind of be. That would kind of be sick. Just playing Doom Eternal until I figure out this min stack question. That'd be so funny. Alright, I'm gonna do it actually. Doom Eternal, here we go. Alright, let's go. Min stack. Alright, so maybe I'll copy this boilerplate code. Ooh. Let's, instead of copying it, write it. You know what I mean? Oh yeah. That's not even what I wanted, man. Alright. Terminal. I feel like this should be pretty easy. I mean, okay, base is the list, right? You want to be able to get the top element of the stack, and you want to get the minimum element of the stack. I mean, this is just... as easy as it gets, no? Let's just not build a wrapper, right? But actually think about how to do this. Top of the stack would mean the actual top value. Right. I'm gonna say, you know, there's something sussy about it. Get min. Minimum element in a stack has to be O of 1. Well, you have to keep track of the min value. I'm assuming that's right. Make this none to begin with. Push, pop, top. Let me think. Push. Yo, that's actually hard for the pop side of things. How can you do this in O of 1 if you don't even know? Yo, this is kinda actually tough. Val, min. Yo, this is actually kind of interesting.
Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve min stack. So this is a pretty good design problem and the description is pretty simple. So our job is to design a stack class that supports 4 operations. Obviously we want to push onto the stack, we want to be able to pop from the stack, and we want to be able to get the top value on the stack. And last but not least, the 4th one, this is the part that's going to be tricky. We want to be able to retrieve the minimum element in constant time. So we want to be able to do all 4 of these operations in constant time. Now, if you are familiar with a stack data structure, you know that by default, a stack will be able to support adding a value, popping a value, and getting the top value, all 3 of those in O of 1 time. Now, I'm not going to go into the details of how to actually implement a stack. You can implement it with a linked list, or you can do it with an array. In this problem, we're basically just going to use the built-in data structure that is pretty much implemented as a stack. But the main part of this problem is being able to do this last operation, getting the minimum value from the stack in O of 1 time, right? Because by default, a stack doesn't support this operation. Now, a stack, let's say we're implementing it with an array. So let's say this is our stack. And let's say we do a few operations. Let's just look at this example, right? We push a -2. We push it, let's say, to the bottom of the stack. We push another value, a 0. We push another value, -3. And now, so we did 3 push operations. Now we want to do a get min. So how exactly are we going to be able to get the minimum here? Well, a naive way would be just look at every single value, -3, 0, -2. So we can look through the entire stack. That's going to be O of n time to get the minimum. So at least we have a baseline. At least we know how to do it in O of n time. That's not too bad, but how can we do better? How can we actually get it to be O of 1? And if you want to try to figure it out yourself, I recommend taking a look at this hint that Leetcode actually provides. They say consider each value in the stack having a corresponding minimum value. Think about that for a second. So let's go back to the basics when we were adding 3 values. So when we first added a value, we added a -2. So what's the minimum at this point in our stack? When we only had 1 value, the minimum at that point was -2, right? When we added another value, we added a 0. What was the minimum at this point? When we added the 0, did this replace our current minimum -2? No, it did not. So in other words, we can leave our minimum as it is, but that's not always going to work. Having a single value maintaining the minimum isn't always going to work, because for example, let's say we added another -2. Okay, our minimum stays the exact same, -2, right? Now what if we pop this -2? Okay, we pop that -2. Now how do we know what's the new minimum? Is the minimum going to stay -2 or is it going to be 0? Well, of course we know it's going to stay as -2, but how can we do that? So a good workaround is, for each position, write down what's the minimum at this point. So when we pop, then we know, okay, this is going to be the new minimum. So let's say at this point, the minimum stays -2. And we added a third value. Remember, we added a -3. So now what's the new minimum? We can compute it in O of 1 time by just comparing this new value we added and comparing the current minimum. Obviously, -3 is smaller, so at this point in our stack, the minimum value is -3. If we were to pop this -3, then the new minimum would be a -2, right? This would be the top of our stack. This would be the minimum so far. So what you might be noticing is on this right-hand side, I'm actually defining another stack, right? We have 2 stacks. One stack is telling us the values that we've added so far in the order that we added them. The other stack is telling us what's the minimum value that we have added so far in each position of the stack. So if we add a value, we'll be inserting into both stacks. If we pop a value, we'll be popping from both stacks. When we get the top value of our stack, right, because remember that's an operation, the top value, we're going to be looking at the first stack. We're just going to say, okay, this is the most recently added value in the stack. When we do the get min operation, we're going to look at the top of our minimum stack, get that in O of 1 time, right? We just have to get 1 value, so we can do it in O of 1 time. Don't have to pop anything. We just have to take a look at our second stack. So that is the main idea. It's a little tricky to actually come up with this, but once you do, it's very simple. So now let's actually jump into the code. Okay, so now let's get into the coding portion. So we know that we have to support 4 operations, and in our constructor,
Alright, well, all of that makes sense. Let's clear out some of these. Okay. My guess is, we have min stack and a stack. push. Problem is, min stack can only be appended when you know for a fact it's greater than the value. So when it's that, or when it's min stack what am I thinking? Min stack dot append. I don't even know what I'm trying to think here. Min stack. Min stack. So, as Leetcode has said, you have some value. If that new value that's coming in is smaller if it's smaller than the value that's going out, if it's smaller than the value, min stack, we append a value, but the value has to be oh yeah. Nah, man. Nah, man. Man. I am cooked. You append the value only when there is a small value. Only when there is a small value. And then you pop only if okay. You pop it off only when the value that's being popped is also part of the min stack. The top is just Am I doing the top of the min stack or the stack? Of the stack, right? Yeah. Is that right? Let's just see. GG. GG. VG. Y. I'm gonna guess it fails. List index out of range. Oh yeah, of course. There's nothing in there. Or would there be nothing in there? Let's see. Input. Min stack. Push. -2. I think I found the answer. Ah, man. I hate this. No, that's not even what I want. That is it, man. I'm so good. I'm so good. Alright. So that means I can also copy all that to here. I'm happy with it. And anyway, he was going to speak
Another
about it.
day, another controversy.
The first thing we're going to do is, since we know we're going to have 2 stacks, let's define those stacks first of all. And like I said, I'm going to be implementing this with an array, or at least an array list. If you are using Java, this is not just an ordinary array. We can append, pop from it. It's basically Python's implementation of a regular stack. We're going to have a second array, which is going to be the min stack. And initially they're going to be empty. So the simple thing to do is push, right? That's the first operation. So on our first stack, it's always going to be easy, right? We're always going to take the input value and append it to the first stack.
I mean, let's
Now,
just have it
with
on the side just for
stack, we need to know for the second stack,
comparison.
if there's already a value inserted in the minimum stack, then we're going to take the minimum of the input value and the minimum value, or at least the value at the top of our min stack, and take the minimum of those two and then append that value to the min stack. So let's update our value first of all. Let's set it equal to the minimum of itself and the minimum of the top of our min stack. So let's say self.min stack at -1. At least that's how you do it in Python. But we know that this min stack actually could be non-empty. So we're going to only do this if our self.min stack is non-empty. Otherwise, let's just take the minimum of val and val. So this might be a little complicated. I probably could have just done an if-else statement, but in Python, I feel like this is a little bit cleaner. So we're just taking the minimum of value and the top of our stack if the stack is non-empty. If it is empty, we're just taking the minimum of val and val, because if the stack is empty, then of course we're just going to take the min stack and append the value to it. Right, so when we append this value, it should be the minimum of the input value and the minimum of the top of the min stack. So that's all for our push function. Now let's do the pop function. We don't have to return anything. All we have to do is pop from our stack, but since we have 2 stacks, we're gonna have to pop from both of these stacks. So popping from the first stack and popping from the minimum stack. So that definitely takes care of everything for us. It feels like cheating since we're pretty much using the built-in functions. And to get the top value of the stack, we are going to take from the top of the first stack, right? By top, we want to get the last value that was inserted, and this is always going to be called when our stack is non-empty, so we don't have to take care of any edge cases. The last one, get min, is going to be returning from the top of the min stack, right? Because we want the minimum value. That's always going to be on the top of the min stack, and this function as well is only going to be called when our stack is non-empty. So that is the entire code. And of course, for some reason, I didn't notice that I didn't actually put the else over here. So if it was confusing before, I'm really sorry about that. So now you can probably tell exactly what's going on because it's pretty simple. So this is what we're going to be evaluating if our stack is non-empty. Else, this expression is going to evaluate just to this value. And then we'll, of course, take the minimum of these two. So now this code is complete. You can see that it's very efficient because every single one of these 4 functions is done in O of 1 time. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.
Time for a little bit of a break. What we're going to do is just watch this R1 video. Reaction time. Now we're just going to be reacting to Fireship's R1 makes Rabbit R1 makes catastrophic rookie programming mistake.
For the Rabbit R1, apparently. This time, its developers wrote some bad code, like inexcusably, catastrophically bad code. Code that allows someone to view every message ever sent on all devices. Code that allows the attacker to alter the messages sent to the end user. And code that can brick every R1 in existence. It's outrageous, egregious, and preposterous.
Lascivious, salacious, outrageous.
But the most shocking part about this story is what the company did to fix it. In today's video, we'll find out how this is even possible so you don't make the same mistake when shipping your own half-baked AI product. It is June 27th, 2024, and you're watching the Code Report. I first encountered the Rabbit R1 at CES in January, where I was blown away by its utter uselessness, along with the amount of cringe buzzwords used by its CEO. Despite setting off my bullshit detectors, these devices sold out pre-orders within the first few minutes. But after the initial hype, the Rabbit R1 has been the lolcow of tech products of 2024. It was exposed as being nothing more than an Android app under the hood. It was revealed to have origins in crypto and NFT scams, and when it actually shipped, it was even more useless than people imagined. But never in my wildest imagination would I expect their developers to make a mistake like this, hard-coding API keys directly into the codebase. This mistake was discovered by a group called Rabbitude, which is dedicated to reverse engineering the R1. According to their statement, back on May 16th, they obtained access to the Rabbit codebase, and inside that codebase, they found hard-coded API keys for 11 Labs, Azure, Yelp, and Google Maps. The most problematic one is 11 Labs, which is an AI text-to-speech platform. When you talk to the Rabbit R1, it turns your speech into text. It then passes that text off to a large language model to generate a response. But before that response goes back to the end user, that text needs to be converted back into speech. And that's what 11 Labs does.
Development of the atomic bomb.
That means the R1 needs to make an API call to 11 Labs for every response ever sent by the R1. And that means if someone ever got the 11 Labs API key, they'd be able to read every R1 response in history, they'd be able to change responses, and they could just delete the AI voices from 11 Labs to brick every single R1 in existence in a matter of seconds. And that is quite the exploit. And just to be clear, it's not 11 Labs' fault. But there's one thing we need some clarification on. In the statement, it says Rabbitude gained access to the Rabbit codebase, which I assume is referring to the back-end Rabbit codebase. The details are sparse, but I don't think they actually put an API key in their Android APK, which would be an even more absurd mistake because you should never put secret API keys in client-side code. Even my 5-year-old knows that. It seems more likely that Rabbit has a leaker, like an employee dumping the code onto a USB and potentially breaking the law to share it. Leaking is a risky business. Julian Assange once leaked war crimes for which he was treated like a criminal. Even Hillary said, "Can't we just drone that guy?" And he just regained his freedom a few days ago. Now the thing is, when those war crimes leaked, the war criminals didn't stop doing war crimes. And what's crazy is that Rabbit took a similar approach. According to Rabbitude, they've known about this exposed 11 Labs API key for a month, and their solution was to just ignore it and hope the problem goes away. This information, I assume, is also coming from the leaker. Now, at this point, Rabbit has rotated its API keys, and this group is operating for the public good, thus nothing catastrophic has happened to user data, but there's a lot of good reasons not to hard-code API keys into your code. In fact, I have a new full Linux course coming up for Fireship Pro members that coincidentally talks about this issue. Might as well leave you a discount code if you want to get early access. An API key is like a password